Let's go over the impulse momentum theory, and now we're getting into a little bit more difficult calculus here. Um, yeah. Let's go with the world idea. Let's say I punch someone in the face. That's really fast, right? I'm punching them in the face, they're getting hurt. I'm inflicting a lot of force onto them in a really short amount of time. So whenever you hit or stop something, a bat on a baseball, I mean, that's also pretty quick. A car crash, the force is not constant. It spikes and then drops. Because the force change, we look at the total effect of that force over the whole time, which leads us to the thing. So, in simple terms, let's say I punch you in the face. Let's do a force times time graph. The force graph is not going to look like this because I'm probably going to hit you with the greatest force when I hit you on impact. When my fist is just falling through, it's probably slowing down a little bit, partially due to the collision, to the collision. It's not going to look like this. It's not going to be the same force throughout, like a hydraulic press or something. It's probably going to look a little bit like this. Oh, wow. Sorry, that looks like the force is probably going to be highest on a certain area because that's where I hit you, and that's going to be where the force is strongest. The force is not uniform, and that's why we kind of need impulse here. So this is kind of complicated because I get into calculus a little bit. Unfortunately, though, or fortunately for us, we don't really have to worry about that. But simply put, if you take that graph here, force is just the area under this curve. And for us, it's a little bit difficult to understand because force times time is kind of abstract, right? F times t doesn't really mean anything. Well, it does actually, but it's hard to understand. Like VT is pretty easy because it's velocity, meter slash seconds divided by time. But what does force times time mean? Well, first it's the area under the curve. And we'll get into the impulse momentum theory in a little bit here. But I just want you to understand that in calculus they would say this. Oh, sorry. Oh, wow. Yes, in calculus they would say the integral. I guess it would be indefinite here. Um, or actually, I guess the bounds, I guess it would just be t and 0. Wait, t and 0. Yes. Of f, capital F of t. So just the area under the curve there. And we'll get to that in a little bit. Simply put, the formula is just impulse, which is force times time, and impulse is defined, I believe, as J. Give me 1 second. Yes, J. And it's defined as F delta T. I don't really like using delta T because I like using T because time is relative everywhere. So between 2 points, time would be relative. So I like using T or the time elapsed. Um, and this would be average force because time is over an interval. But we can also apply this to calculus. In fact, you could just do average force times T, um, which would be the same as this. But we can also do the summation of the forces, or force times T, I guess kind of like Riemann sums. So like the instantaneous force, which I'll just do as instantaneous force plus T, sigma notation as T approaches 0. So just it's just gonna under here, if you learn calculus, it's just gonna be really small strips. Our rectangles here, but we're not gonna really focus on that. We're just gonna focus on average force times t because we can make the instantaneous force average force times t by just calculating the area under the curve and dividing it by time. So yeah, that's what impulse is. But we'll get into a little bit of what it actually means. But right now, just note that impulse is just force applied over time. That's all it means. But we'll get into more. I think it's J. Yeah, sorry, J. I keep using J or I because of impulse, but the actual formula is force times time, as we mentioned before. Average force, because average force times time will always give us the force under the curve. So if we assume like a hydraulic press where the force is even and localized, or not localized, but even, it's always just going to be average force, which is going to be AVG F times T, which will give us the force over time under the curve. It's much like work, which equals force times distance. The work isn't uniform, sorry, the force isn't uniform throughout. It could be applied at different intervals, but it's the same thing as an average force times distance. So linear momentum is just defined as mass times velocity. In fact, the formula would just be P equals mv. And we'll see how they defined it. Where the linear momentum vector has the same direction as the velocity vector. So let's go over the derivation here, and it's quite simple actually. So everyone knows that force is just equal to mvf minus vo over t. Now here's the issue here, or not the issue. This one assumes a constant acceleration because it's splitting the acceleration into constant. So this would be average acceleration. So that would be average force as well. So we could just times t on both sides, giving us f average t equals vf minus vo times t, which this is just impulse. So impulse is vf minus vo. And we can rewrite this as force average, which is just going to be m times the average acceleration times the time equals this. And we can cancel out mass from both sides, leaving us with the acceleration average times time is equal to the change in velocity, which guess what? That's the first kinematic equation. So that's just simple logic there. But let's go over the nuance of this formula. So if we go over force times distance, or J, is equal to mvf minus, or plus v, oh no, minus, sorry, minus mvo, which is quite simple. I just distributed it from the mvf minus vo. So same thing here. I'll just actually put it like this so we can see easier. So what happens if the time is greater? Well, if the change in this velocity, let's just say, is a constant. So let's say that the delta v, or this term right here, is just t. Well, yeah, we'll just do t equals ft, right? Oh, sorry, let's not use t because we'll do d. That means the greater the, and mass is constant here, so it's just a multiplier. So the greater the time is, the smaller the force will be, because if this is a constant here, then the greater this is, the smaller this has to be to balance it out. So that means the greater the time, the lower the force applied over that interval is, or not really that, because that would be impulse, but the lower the force is. So let's take the area under the curve here. This is the same amount of impulse as this, which this would just be t over 2, so the time over 2, and this would be time times the force over 2 times force. This is the exact same thing, because if we plug it into the formula, we get f of t over 2, f over 2 divided by t. So this is the same exact impulse, but this has greater time, meaning that this is applying the force very smoothly over the interval. So think of this as like me pushing something very lightly. I'm applying a force to like a box very lightly, as opposed to me just like running through, applying a force of maybe like 100 newtons. Oh yeah, I guess we can, since we applied a number 50 newtons over 10 seconds, and then 100 newtons over 5 seconds. Mathematically, these are the same impulse, but this one is much more steady. I'd rather be pushing it like this, because like this, I mean, I guess you can lose some to heat and stuff and other forces, but this one's a little bit more lax and chill. So yeah, it's basically the logic there. I mean, the greater the time, the average force is smaller, and likewise, if we make the time smaller, then we'll have to have, if for the same area, we'll have to have a greater force. Meaning that the shorter the force, the greater, I mean, the same impulse, but the greater the amount of force applied during that small interval. So yeah, that's the logic behind the thing here. And if we were to apply this general impulse formula to calculus, so J average equals M. I don't want to say A average, actually, because it's not average. It would be the same as M times the summation, I believe. Wait, yes, the summation. Actually, not even the summation. Yes, wait, the summation. Or I guess we have to come here, which is just going to be force. Yes, force times t as, that's not a function, by the way, it's just force times time as t approaches 0. Because then if we take under that curve, remember it's just smaller and smaller intervals, is equal to the mf minus vo. So same exact logic here, except that we use average acceleration just for simpler notation and note taking, but the thing applies to the other one. So yeah, that's the logic there.